You can see here, functional skills, no. GCSE could be, so this is what we're going to be taking a look at. Quick search on the net revealed this here, GCSE, and hang on a minute, where's the, that's what I want. And we come down here. You can see that for the cone, they've actually given you the equations. Surface area of the cone, that's this sort of funnel shaped area here, is that, and the volume is that. Well, we're just going to be talking about substitution basically. Do I do the volume? Do I do the volume? Yeah, we can substitute. I'm not going to use these numbers. I'm going to use some of my own. If we take a saw and cut downward through the point all the way down to the bottom, we end up with this here, not to scale of course, there. Now in this instance they're not taking into account a base, you know, but I am going to, so slicing it all the way down, you would in fact have a bottom to it like that. Not to scale, this is meant to be exactly in the center. So let's just draw that again, half of it. So we have the red line, we have the base, and we have the center line, which I'm going to do as dotted. Now I'm going to pick numbers such that, remember this is not to scale, the size of that is 3, the size up here, the height, is 4, and I can tell you now, if that is 90 degrees, the length of this slope here is 5. Pythagoras, do you remember Pythagoras? 3 squared plus 4 squared equals 5 squared. Now let's see if that's true, shall we? Let's see if that is indeed the case. 3 3s are 9, 4 4s are 16, equals something. 9 and 16 is 25, so that becomes 25, and the answer there, 5 squared, is 25. So the left hand side equals the right hand side, so it is true. Okay, Pythagoras works certainly in this condition here. So what sizes am I going to choose? Oh, I've already done that, haven't I? Silly me. Okay, here's the center line. Cutting down from there. There's the edge there. And I'm going to make that 3. So the height, vertical height, is 4, and as demonstrated, the slope is 5. In the formulae they made that L, and they made that R for radius, L for length I suppose, R for radius, and they said that the surface area of just the red part all the way round, you know, is the area of the top. Let's do it in the same color, shall we? Let's do it in the same color. So we've got the area of the red part of the cone is pi radius times the length. That's the radius length. So we just substitute in. Pi is pi, it remains as it is. R we said was 3, white. And L is 5, so we put in 5. This will now give us pi times 3 5s are 15, except normally we write it as 15 pi. That's because it's traditionally done that way. So that is the area of the cone part. This part here, the funnel part. But I said I wanted to also do the base. See, this is how substitution works. You just put the numbers in where they should be. Where there's an L, should be a 5. Where there's an R, there's a 3. There's meant to be a multiply in there. You just multiply them together and you get your answer. So that is the area of the cone part. What about the circle part? What about the circle part? Well, the area for the circle is pi r squared. Okay, pi is pi times r, and r we know is 3 squared. So that gives me pi times 9, which is normally written 9 pi. Normally put the number first. So the area of the base of the cone is that. Total area you add them together. You got 15 lots of pi. That's a lot of pi, isn't it? Oh, steak and onion pie. Put with 9 lots of pi. So we've got 15 of these, put with 9 of these, add 9 and 15, and we get 24 lots of pi. Right, so the total area of the cone, the funnel part, added to the total area of the circle base gives me 24 pi. The reason we do that is because it is precise. If we have whoa, come on, thank you. Pi, look, pi is one of those special numbers. If I do shift pi and do equals, convert that to a decimal. Now these numbers here go on and on and on and on forever and ever and ever with absolutely no repeats. Okay, if it stops at some point, it's called a terminating decimal. This goes on and on and on. So as soon as you round it, you introduce an error. That is precise. If I were to write 3.1416 as an approximation of pi, it is not precise. Normally when you do that, you say rounded to 1, 2, 3, 4 decimal places. That tells them that you've rounded the number so that this is not exact. That is exact. Very important facts. Substitution, when they give you the formulae, is fairly straightforward. Sometimes you get very complicated formulae, but not at this level. Believe me, some of them can get horrendous. That's fairly straightforward. As before, we get a saw, we cut right down from the point, and that's meant to be a straight line, and we get that shape when we look at the cut area. So we want the volume of the whole thing. Now we said that the radius, which is from there to there, was 3. From there to there, we said was 4. And and along the slope is 5, which equals L. This one equals R, and that one we will call height. That's the normal type of notation they use. Volume. Now, the formula for volume that they gave us was 1/3 pi r squared, that's the area, isn't it, times the height. So we're using this one now instead of that one. We just substitute in. We have 1/3 is 1/3, that doesn't change, times pi, well that is pi, times r is 3, so we have 3 squared, we've got to square it, multiply that by the vertical height there, which is 4. So we end up with, oh yeah, look at this, 1/3 times pi times 3 times 3 times 4. Those two cancel out, so we end up with just pi times, that's gone, 3 4s are 12. So what we end up with is 12 pi. And that is the volume of this particular cone. Straightforward when you just put in the numbers. I call it plug and chug. Okay, so you plug the numbers in, you chug your way through the equation, and you get your answer. Fairly straightforward once you know what you're doing. Right, not very well drawn. One sphere. That's the centre of the sphere. So from the centre to any point on the surface of the sphere, you know, a ball, the radius I'm going to set at 3. Now I'm glad I picked 3 because it showed something up that I wasn't aware of before, and we're going to be looking at that as well. Alright, we want surface, I'm going to S dot surface area. The equation for that is equal to, if I remember correctly, 4 pi r squared. Look, that bit there is the area of a circle. Right, so the surface area is 4 times the area of the circle, and yeah, we just pump the numbers in. You know, we got the 4, we're told that. Stick with the symbol pi rather than try and use fractions, because that is precise. R, we know R is 3, so it is times 3 squared. Well, that is 4 times pi. 3 times 3 is 9. 4 times 9 is 36 pi. So that is the surface area of a sphere with the radius being 3. Volume. Again, with the radius being 3, the volume starts with a 4 again, but it's 4/3 pi r. Notice the structure here is the same as the structure there. So this time it is cubed. 3-dimensional, 2-dimensional. Surface area is yeah, okay. Just remember that one is squared and this one is cubed. Alright, so pump in the numbers. We got 4/3 times pi. You know, we're just substituting in. There's the 3 times 3 raised to the power of 3. If you like, this is 4/3 times, I'll move that so it's in there. You can do that with multiplication. 3 times 3 times 3. Now the pi times pi. Cancel, cancel. So this becomes 9. 9 times 4, 36. There's the pi. Really? Absolutely. Absolutely. That roused my curiosity. Take a look at this. I used Excel and I experimented. Radius first, column A, I went 1, 2, whole number of progressions. So it's sequentially increasing there. I worked out the surface area using the formulas we just used, and the volume, the formula we just used. There's the 3. That is confirmed in Excel. Now to test for scale, I've done volume divided by surface area. Here we are, volume divided by surface area. So if it is 1, they're the same size. If it is 2, the volume is twice as big as the surface area. If it is 3, the volume is 3 times as big as the surface area. But progress, look, 1, 2, 3, then the next one. Or if you like, we'd start 1, 2, 3, 1, 2, 3, 1, 2, 3. Look at these numbers here. I've converted them to fractions. 1/3, 2/3, 1/3, 2/3, 1/3, 2/3. There's a definite progression there, isn't there? There's a link. Now on the spreadsheet I had volume divided by area. Okay, which we can represent as a ratio in fraction form as volume divided by area. Okay, so yeah, by dividing that into that, we're doing the equivalent of some number there with 1 underneath. So we are saying it's that much bigger than this, or that much smaller than this, depending upon the values we get. Okay, so the volume equation is equal to 4/3 pi r cubed. Area is equal to 4 pi r squared. So we end up with this. Volume divided by area, 4/3 pi r cubed. Divide that by 4 pi r squared. I can write this bit here as 4 pi r cubed all over the 3, which then is divided by that, which is the same as multiply by. Hang on, if I do that, you've seen me do this before, divide, change the sign to multiply, turn that upside down. So we have 1/4 pi r squared. Okay, let's cancel out a little bit. The 4's are gone, the pi's are gone. So now we are left with, the only thing on this side is r cubed times 1, so it is r cubed. And that is over 3 times pi, 3 times r squared, 3r squared. Now that is the same as r times r times r. Underneath we have 3 times r times r. Cancelling out, we end up with r/3. Hence the thirds in the progression.